Let the weight of your body be taken by whatever is holding it up. The mattress underneath you, the pillow, the blanket. None of it needs any help from you. Breathe out slowly, and let the out-breath run a little longer than the in-breath. Again, slower. Once more, and then let the breath go back to whatever pace it wants. Bring your attention down to your feet. Not to move them. Only to notice that they are there. Let them be heavier than they were a moment ago. The ankles. The shins. The calves, which hold tension long after the day is over. Let the calves go soft. The knees. The long muscles of the thighs. Let them spread out and stop working. The hips, which carry the whole weight of sitting. Let them settle. The lower back. Let it lengthen without effort. The belly, rising and falling on its own. The chest, wide and slow. Your hands. Let the fingers uncurl a little. The wrists. The forearms. The upper arms, heavy against your sides. The shoulders. Let them drop away from your ears. Let them drop a little further than that. The neck, front and back and both sides. The jaw. Let the back teeth come apart. The tongue, resting on the floor of the mouth. The cheeks. The small muscles around the eyes. Let the eyes be still and soft behind the lids. The forehead smooth. The scalp loose. Now the whole body at once, as one single weight, held up entirely by the bed. Nothing to hold. Nothing to solve. Nothing to remember. What follows is a long, slow story about a piece of clay the size of your hand, and a question that has been argued over for 80 years. You do not have to follow it. It will go on whether you do or not. On the 6th floor of Butler Library, at the northern end of Manhattan, there is a slab of fired clay about 5 inches across and 3.5 inches tall, roughly the size and heft of a paperback with the pages torn out. Its surface is sand-colored, blotched with rust orange and black where the firing caught it unevenly. There are a couple of serious gouges. Down the left-hand side, there is no edge at all, because the left-hand side is gone, broken away cleanly at some point in the last 3,800 years, taking with it an unknown number of columns of writing. What survives on the front is 4 columns of numbers, ruled into 15 rows. On the back the ruling continues, and there is nothing else at all. Its catalog number is Plimpton 322, after the New York publisher who bought it in the 1920s, and there is no agreement about what it is for. Those numbers are Old Babylonian, which is a period label covering southern Iraq from about 1900 to about 1600 years before the Common Era. They are written in cuneiform, pressed into wet clay with the cut end of a reed. Only two shapes appear in the entire number system. A thin vertical wedge stands for 1. A wider corner wedge, tipped over, stands for 10. Everything is built from those two marks. 3 verticals in a row make 3. 2 corners and 4 verticals make 24. Counting is purely additive up to 59, which is 5 corners and 9 verticals crowded into one space. And then something happens that no other ancient system did in quite the same way. At 60, the scribe moves left and starts again. Babylonian arithmetic runs in base 60, with place value, exactly the way modern arithmetic runs in base 10. Units come from the rightmost group of wedges. Move one group to the left and it counts 60s. One more group left and it counts 60 60s, which is 3,600. That system is older than the tablet, reaching back through the accounting practices of the Sumerians and earlier people in the same region, and it survives today in the only 2 places it never got replaced: minutes and seconds of time, and minutes and seconds of arc. 2 features of it will matter a great deal later. First, there was no zero. Not in this period. A scribe writing a number with nothing in the 60s place simply left a gap, or did not, and the reader worked it out. A sign for an empty place does eventually appear in Mesopotamia, in the last few centuries before the Common Era, and even then only in the middle of a number, never at the end. Second, and stranger to modern eyes, there was no decimal point. A string of wedges reading 1, then 24, might mean 84, which is 160 plus 24. It might mean 5,040, if the one is shifted one place further over and counts 60 60s. Nothing on the clay resolves it. Only the scribe knew, because the scribe knew what the problem was about and roughly how big the answer ought to be. And everyone reading the tablet was in the same trade with the same expectations. Scale was context, not notation. Consider one number that a scribe wrote down in this way: 1, then 24, then 51, then 10. Read as a whole plus 3 descending fractions. It comes to 1.414213, near enough. It is an approximation of the square root of 2, accurate to about 1 part in 2 million, and it sits on a small round tablet in the Yale collection. That tablet is a palm-sized disk, the shape a student produced rather than the shape an archive kept. Scratched onto it is a square with both its diagonals drawn in. One side is labeled 30. Along a diagonal are 2 more numbers. One of them is that approximation of the square root of 2. The other is the same value multiplied by 30, giving the length of the diagonal itself. Somebody drew a square, labeled the side, and correctly computed the diagonal. Pythagoras was born something like 1,200 years after that clay dried. Long before any Greek wrote it down, Mesopotamian scribes knew and used the relation between the sides of a right triangle and its diagonal, and dozens of surviving tablets treat it as routine. What there is no evidence of, anywhere in the cuneiform record, is a proof. Babylonian mathematics is procedural. Do this, then this, then this, and the number you get is the answer. Proving a general claim once and for all from stated assumptions, so that the question closes forever, is a Greek habit of mind, and it is genuinely not present here. Scribes had the fact and used it constantly, without ever having the theorem in the sense that word later acquired. The Yale disk shows something else too. The historian David Fowler and the Assyriologist Alina Robson looked closely at that square root and concluded the student almost certainly did not calculate it. He looked it up. Constants like that circulated in coefficient lists, reference tables of useful numbers, the ratio for a diagonal, the ratio for a circle, the volume factor for a pile of bricks. This was a profession with handbooks, and the long argument about the broken slab in Manhattan is, at bottom, an argument about what kind of handbook it is. Its modern history starts with a man named Edgar Banks. He was American, briefly a consul in Baghdad, an excavator for a while at a dig in southern Iraq, and for years afterwards a dealer who sold antiquities by mail in small batches to American colleges and seminaries and libraries. A trade that violated Ottoman law, and that has left several thousand tablets in American collections with no find spot and no excavation record. In 1923, he sold 5 tablets to George Plimpton, a New York publisher, for a combined price of $10. Plimpton was not collecting Babylonian mathematics. He collected the history of education, textbooks, primers, copybooks, the physical residue of teaching. He left the whole collection to Columbia shortly before he died in 1936, where it sat under his own catalog numbers, which is how the most argued-over mathematical object in the ancient world came to be named after a publisher, and filed as item 322. Banks's price list said the tablet came from the mound covering the ancient city of Larsa. A dealer's claim on an undated piece of paper is worth roughly nothing on its own. It is held up anyway, for reasons that come from the tablet rather than from Banks. For 20 years nothing much happened. Then in 1945, 2 historians of science, Otto Neugebauer and Abraham Sachs, published it in a volume of mathematical cuneiform texts, and what they saw in those 4 columns was arithmetic that had no business being there. Of the 4 surviving columns, the second gives the short side of a right triangle, and the third gives its diagonal. The long side is not on the tablet, but it can be recovered, and when it is, every single row turns out to be 3 whole numbers where the square of the first plus the square of the second equals the square of the third. Pythagorean triples, and mostly enormous ones. Row 4 gives 12,709, 13,500, and 18,541, and the first 2, squared and added together, come to exactly the square of the third. Numbers that size are not found by trial. Neugebauer and Sachs proposed that the scribe had generated them systematically, from a pair of starting numbers combined by a fixed recipe that always yields a matching triple, which is the construction that turns up much later in Greek number theory. On that reading, Plimpton 322 became the oldest known document of number theory in the world, by about a millennium and a half, and that is how it entered the general culture. A Babylonian, working around 1800 before the Common Era, was doing pure mathematics for its own sake. There is a wrinkle in the tablet that this reading has trouble with, and it sits in row 13. One of the numbers, there is not the value that belongs in the table, but the square of that value. Somebody did a multiplication, and then failed to take the square root at the end of it. 2 other rows have mistakes of a different kind. The number theory reading held for more than half a century. What eventually cracked it was philology, the close study of the actual words on the tablet rather than the numbers. Eleanor Robson trained in the language and the material culture rather than in the mathematics. And in 2 papers published in 2001 and 2002, she went at the tablet from that side. The first was called Neither Sherlock Holmes Nor Babylon, and the title is the argument in miniature. A Sherlock Holmes approach treats an ancient text as a self-contained puzzle to be cracked by anybody clever enough, with whatever tools are to hand. Robson's objection is that this method has no way of being wrong. Any sufficiently ingenious modern reconstruction will produce the numbers on the tablet, because the numbers are true and mathematics is consistent. Reproducing the answer proves nothing about the method that was actually used. So she set out tests that any interpretation has to pass. It has to use techniques documented elsewhere in the old Babylonian record, not techniques that merely work. It has to account for every heading and every number, including the ones that are wrong. It has to respect the physical tablet, including the fact that it is broken and that something is missing. And it has to fit the conventions of the genre, the way tables of this period were laid out, ordered, and headed. Then she read the headings, which is the part the mathematical treatments had mostly skipped, because they are damaged and technical and in a dead language. Of the 4 columns that survive, the 4th is easy. Its heading is a Sumerian phrase meaning its name, and the column holds nothing but the row number, 1 through 15. Columns 2 and 3 are headed with phrases meaning the square side of the short side and the square side of the diagonal. Square side is the Babylonian term for a square root, the side you would need for a square of that area. So those 2 columns give the shorter leg of a right triangle and its longest one. It is the first column's heading that matters, and it is broken. Robson's restoration of it reads, roughly, the holding square of the diagonal, from which one is torn out, so that the short side comes up. That describes a procedure, rather than a quantity. Something is being held, something is being torn out of it, and something comes up as a result. The word doing the work is built from a verb meaning to hold, and it names a square that is constructed and held while you operate on it. Start with reciprocals. The reciprocal of a number is whatever you multiply it by to get one. Division, in a place value system, is awkward, and multiplication is easy, so the standard Mesopotamian move is to turn every division into a multiplication by a reciprocal, and to have the reciprocals memorized. Reciprocal tables are among the most common school texts that survive, each line reading, "The reciprocal of this, its reciprocal is that." But only some numbers get onto the list. In base 10, some fractions terminate and some do not. A half is not 0.5. A quarter is not 0.25. A fifth is not 0.2. A third is not 0.3333, forever. 10 factors into 2 times 5, so a denominator built only out of 2s and 5s divides cleanly. Any other denominator will not. 60 factors into 2, 3, and 5, with the 2 counted twice. 3 different primes, against 10's 2, and that one extra prime changes the texture of arithmetic completely. In base 60, a third terminates. It comes out to exactly 20/60ths. So do a 6th, a 9th, a 12th, and a good many others. Numbers whose only prime factors are 2, 3, and 5 are called regular, and regular numbers are the ones with reciprocals you can write down. 7 and 11 and 13 run on forever, and are simply absent from the tables. So an old Babylonian scribe lived in an arithmetic world sorted into 2 kinds of number, the ones that behave and the ones that do not, and that distinction organizes the entire discipline. The second piece of background is what happens when a scribe wants to solve a quadratic. And here the reconstruction is largely due to the historian Jens Hoyrup, who spent decades arguing that the old Babylonian problem texts are not algebra written out in words. They are geometry written out in words, describing actual cut-and-paste operations on actual rectangles. His clearest example is a different tablet in the Yale collection, not the round disk, but a plain column of figures, probably from Larsa within a few decades of Plimpton 322. The problem it poses is this. A number and its reciprocal differ by 7. Find them. In problems of this kind, the number and its reciprocal are both stretched by a common factor, so that, multiplied together, they give 60 instead of 1, the same relationship, just scaled up, and a convention of the genre. In modern notation, that is a quadratic equation. The tablet does not do it that way. Its steps are worth hearing once for the shape of the thing, rather than for tracking every number. Take the 7 and break it in half, giving 3½ Square the 3½, giving 12¼ Add the 60 that the 2 numbers multiply to, and you have 72¼ Take the square side of that, which is 8½ Add the 3.5 back to get 12. Behind it is a rectangle 60 units in area, longer in one direction than the other by 7. The excess strip comes off, gets halved, and 1/2 swings around to the adjacent side, so the same area is now an L shape with a square bite missing from the corner. Patch the bite, complete the square, and the side of that completed square is what you were after. Completing the square is an instruction to complete a square here, not a figure of speech. Robson's reconstruction is that the broken-off left edge held a reciprocal pair. A number and its reciprocal, side by side, running down the tablet in descending order. At the top, 2 2/5, paired with its reciprocal, 5/12. At the bottom, 1 4/5, paired with 5/9. 5 of those 15 pairs appear on the standard schoolroom reciprocal table. The other 10 show up elsewhere in Mesopotamian mathematics, in the more advanced material for finding reciprocals of larger regular numbers. Take any one of those 15 pairs. Subtract the smaller from the larger and have the result, and that is the short side. Add them and have the result, and that is the diagonal. These pairs are left unscaled, multiplying to exactly 1 rather than to 60, and the long side of the triangle is simply 1 throughout. That is the shape of the setup. The enormous whole numbers on the tablet come afterwards, from multiplying each triangle up until every side is a whole number. Do all that, and out come the values in columns 2 and 3, exactly, with no rounding anywhere, for every row. And the first column, the one with the strange heading, holds the intermediate quantity from the completing the square step, which is why its heading describes a procedure. The holding square of the diagonal, with 1 torn out of it, leaves you the square on the short side. What the table records is a single quadratic setup, run 15 times, with 15 different well-behaved starting pairs. Every technique in that reading is documented elsewhere. Every heading is accounted for. The missing columns are reconstructed as something that genuinely belongs in a table of this genre, rather than as a blank space to hang a theory on. And it explains row 13. Forgetting to take a square root at the end of a computation is not a mistake anyone can make while transcribing a list of triples out of another list of triples, because at no point in copying is a square root being taken. That error only happens mid-calculation. The other 2 bad rows are of a piece with it. A scribe trying to shorten his notation broke a number into factors 1 step too far and lost track of where he was. Those mistakes are a fingerprint of the method, and the method they point at is the reciprocal and completing the square route rather than the recipe Neugebauer and Sachs had in mind. Robson's conclusion is less dramatic than the thing it replaced, and, in its way, more interesting. Ruled columns, a header row, a running index down the right-hand side, that is the layout of an administrative account table, the sort of thing a temple bookkeeper produced. The content is 15 worked instances of one problem type. In short, it looks like a teacher's crib sheet. 15 sets of starting values guaranteed to produce clean whole number answers, so that a teacher could set the same exercise 15 times over and check his students' intermediate steps without redoing the arithmetic himself. Her sentence for it is that the tablet would have enabled a teacher to set his students repeated exercises on the same problem, and to check their intermediate and final answers without repeating the calculations himself. She calls it a teacher's problem list, and says flatly that its author was more likely a teacher than a mathematician of any kind. There is a documented world for that person to live in. In the first months of 1952, excavators at Nippur, a city north of Larsa, dug out an ordinary private house from the old Babylonian levels. It has been known ever since as House F, and it held something over 1,400 tablets and fragments. There were benches in the courtyard, and a basin lined with bitumen holding fresh clay mixed with crumpled-up old tablets waiting to be soaked back into workable material. The tablets are overwhelmingly school exercises, and Robson used them to reconstruct the curriculum. First the physical technique of making wedges, then long thematic vocabulary lists, then weights and measures alongside the multiplication and reciprocal tables, then model contracts and Sumerian literature. Many of them carry a teacher's model at the top, with a student's shakier copy underneath. Somebody lived in that house and taught in it, shortly after 1740, before the Common Era. Nippur is a different city from Larsa, and House F simply shows what a teaching household of the period actually looked like. The date for Plimpton 322 comes from somewhere else, and it has nothing to do with the dealer's price list. Robson's grounds are internal. The tablet's format matches dated administrative tables from Larsa, and the vocabulary of that first heading, built on the same verb meaning to hold, matches two other mathematical tablets from the Larsa region. On that basis, she puts it in the 60 years or so before Hammurabi of Babylon besieged and took Larsa. Larsa's last independent king was Rim-Sin, and his city held out for 6 months. Conventional chronology puts that siege at 1763 before the Common Era. A caveat comes with every Mesopotamian date of this period. Rignall lists are internally consistent, but only loosely anchored to anything astronomical, and specialists disagree about how to hang the whole second millennium onto absolute time. Hammurabi reigning from 1792 to 1750, Larsa falling in 1763. Those figures belong to what is called the middle chronology. A rival scheme shifts everything about 64 years later. The sequence of events is solid, and the century it sits in has a margin. So the settled scholarly position, by around 2005, was a teacher's worksheet generator from a city that had a few decades left. In August of 2017, it came back into the newspapers, because two mathematicians at the University of New South Wales in Sydney, Daniel Mansfield and Norman Wildberger, published a paper in the same journal Robson had used, arguing that Plimpton 322 is a trigonometric table. Their case rests on something real. Because every long side in the table is a regular number, every ratio you can form from a row terminates. It stops. It can be written down completely, with no rounding and no error anywhere. That is not true of any modern trigonometric table, because the sine of an arbitrary angle, the standard ratio used in measuring triangles today, is a number that goes on forever and has to be cut off somewhere. Their paper states it directly. All the values in the tablet are exact, and this distinguishes it from every modern table of the same kind. That property is real, and it is a consequence of the deliberate restriction to regular numbers. From there, they argue that the 15 rows step through a range of triangle shapes, from nearly square to considerably elongated, and that a surveyor or builder holding this table could look up a shape and read off exact ratios without ever extracting a square root, the practical bottleneck in all of this arithmetic. They connect it to old Babylonian rectangle problems on other tablets, where somebody measures two sides of a field and needs the diagonal. 3 objections followed, and the first is that the word trigonometry is doing an enormous amount of work. Trigonometry, as the term has meant for 2,000 years, is the measurement of triangles by way of angles, and an angle is defined by rotation about a center, the way a clock hand sweeps around its pivot. Robson's earlier work had already argued that Mesopotamian geometry works on a different logic entirely, naming and defining plane figures from the outside in. A circle is a thing that curves, named for its circumference rather than for its center and radius. Her argument runs in 3 steps. Mesopotamian scribes never thought of a circle as a rotating radius. Without a rotating radius, there is no conceptual framework in which a measured angle can exist. Without measured angle, there is no trigonometry. Ratios of sides are ratios of sides, and calling them a trigonometric function imports a Greek framework into a place where its foundations are missing. A second objection concerns where the framework in the paper came from. Wildberger is the author of a program he calls rational trigonometry, replacing distance and angle with two quantities of his own devising and avoiding irrational numbers on principle. Irrational numbers being ones like the square root of 2 that never terminate in any base at all. It is his own project, published over the previous decade, and it has found very little uptake among mathematicians. The paper's reading of the tablet is framed in exactly those terms, and it says outright that the tablet resonates with modern investigations centered on rational trigonometry. Evelyn Lamb, a mathematician writing at the time, made the obvious point. A reading that happens to conclude that a 4,000-year-old artifact vindicates the author's own unpopular framework deserves more skepticism than it got. Lamb's third objection was to the publicity, which had outrun the paper. Press coverage, including the university's own, claimed that Plimpton 322 is the world's only completely accurate trigonometric table, and in some respects superior to modern trigonometry. It contains known errors. A document with arithmetic mistakes in it is not the most accurate anything. And the argument that base 60 is uniquely hospitable to exact fractions was being made by counting base 10s, exact fractions ungenerously, and base 60s generously. A thumb on the scale rather than a fact about number systems. None of that touches the structural observation underneath. The table is exact, and its exactness was built rather than stumbled into. 4 years later, a different tablet complicated the teaching reading. In 1894, a French expedition digging at Sippar, in central Iraq north of Babylon, pulled up a small tablet that was catalogued, partially published by its excavator, and then essentially left alone for well over a century in the Istanbul archaeological museums. It is known as C427, and Daniel Mansfield produced the first complete edition of it, publishing on air in 2021. C427 is a field plan, a legal document recording the boundaries of a piece of land after part of it had been sold off, with the geometry of the division written out. No other document of its kind is known from the Old Babylonian period, and its measurements are unusually precise, as they would need to be in a document whose whole purpose is to be produced in an argument about where somebody's boundary runs. The interesting part is how the surveyor laid out his right angles. He used two well-known triples scaled up, 5, 12, 13, and separately 8, 15, 17. Both of those have short and long sides that are regular numbers, so they can be multiplied up or down by any convenient factor and stay exact. Mansfield's argument is that this is no coincidence. A surveyor pegging out a perpendicular boundary needs a triple, and needs one he can rescale freely to fit the field in front of him, and that means one built from regular numbers. Plimpton 322 is a systematic search through exactly that family. So the tablet might be, in his phrasing, a theoretical investigation into a problem arising from land measurement, with the scribal profession working out in the abstract which rectangles are available to a surveyor who needs everything to come out even. That sits between the pure number theory of 1945 and Robson's classroom. The table is theoretical, but the theory has a job. Mansfield is careful in the paper, in a way the press releases were not. He writes that these are conjectures, and that definitive answers to questions of this kind are not available. A surveyor's tablet from Sippar and a table from Larsa a century or so apart are linked by context, not by documents, and nobody has found the scribe's notes explaining himself. 3 live readings, then, 80 years apart, and they are less opposed than the coverage of them suggests. Neugebauer and Sachs were right that the rows are Pythagorean triples, and that they were generated by a systematic procedure. Robson was right about which procedure, right that the object is a piece of professional equipment rather than a work of pure research. and write that the errors prove somebody was calculating rather than copying. Mansfield may well be right that the reason anyone cared about this particular family of numbers is that it was the family useful for laying out fields. A teacher's crib sheet and an investigation of a surveying problem are not exclusive, since the students being taught in scribal schools like House F were going to spend their careers measuring fields and dividing estates. What every reading agrees on is the selection. 15 rows. 15 reciprocal pairs, in descending order, every one chosen so that both members of the pair, and every quantity derived from them, factors into nothing but 2s and 3s and 5s. Not 1 7. Not 1 11. Somebody sat down with a reed and a lump of wet clay, searched a space of numbers for the ones that terminate, ruled the results into columns 15 times over, and got 3 of them wrong. The relationship between the sides of a right triangle was old news, and everybody in the profession used it daily. The question that produced this object was which rectangles have a diagonal you can write down exactly. In a system with no zero and no way to mark where the whole numbers end and the fractions begin, where the same string of wedges could mean 84 or 1 and 2/5 depending on what you already knew. The difference between a number that terminates and a number that does not is the difference between an answer and an approximation. It is the central practical problem of the whole discipline. Robson has a name for the older approach she was arguing against. She calls it rationalist reconstruction, lifting the tablet's numbers out of their cuneiform, rewriting them in modern decimal notation, and then asking what a mathematician would have been doing with them. What that recovers, reliably, is a picture of mathematics resembling the mathematics of whoever is doing the reconstructing. Number theory in 1945, applied trigonometry in 2017. Her own paper ends on the flattest possible version of the point. Any resemblance Plimpton 322 might bear to modern mathematics, she writes, is in our minds, not his. Still missing is the broken left edge and whatever was written on it. If Robson has it right, it held the reciprocal pairs, and finding it would settle from the clay itself, a question that is currently argued entirely from indirect evidence, from format and vocabulary, and the pattern of 3 mistakes. The scribe who made the thing was solving a practical problem, in a city that had about 60 years left, and the evidence for what the problem was is the 15 numbers he chose.